So thank you everyone for coming to the Autodesk Vision Series. This one is on visual effects, and I am Marcus Nordenstam. I'll be presenting some of the stuff we're working on and some of our thoughts and philosophy behind what we're doing and what you'll see in the upcoming world of Maya. So I'll get right to it. Just a quick agenda here, basically how I got into visual effects, and then talking a little bit about what the problems for FX are in my experience, and how I think FX assets can solve some of these problems, what the future workflows in visual effects might be that we're looking at, and also looking at a little bit into the past and the future, kind of meeting Nyad and Bifrost. Nyad, of course, was the precursor in some sense to Bifrost, and followed by Q&A. How I got into visual effects. So basically, I was working in the graphics community, doing a lot of real-time, some flight simulation stuff and other things when The Matrix and The Lord of the Rings came out. And like I think a lot of other people, I was really inspired by those movies, in particular the use of computer graphics and other things. So since I was already in the field, I was like, it's time for me to get into that. I'd always loved film as well. So that was really the reasons I got into visual effects. And my first job was at ILM, so I worked on Star Wars and Van Helsing, and also worked down at Sony ImageWorks. And I was really at the time getting into computational physics and geometry, so I started working on simulation technologies at these places. And in 2004, we won the Oscar for Spider-Man 2, and that photo is really just proof that I'll never win an Oscar, because of course the Oscar went to the supervisors, as it should. And there's a curse in Hollywood, you know, if you touch an Oscar statuette that you haven't won, you'll be cursed and you'll never win one. Well, I've touched two, so there goes that. And then I went to London and worked at Double Negative Visual Effects, where I wrote or co-wrote the Squirt fluid solver, which they're still using, I think, at least maybe here and there. They have newer stuff now, but it was used for a lot of films, Harry Potter, Hellboy 2, But That Rocked, and other stuff. And then one of the things about that solver was the fact that it really, I think, to some extent changed, or I observed sort of how one new technology, this being fluid simulation applied to fire and smoke, how it really changed their ability to compete and the types of effects they could do. It won them a lot of jobs. And so I thought, you know, there's kind of a big gaping hole in the community. No one really has a solver that can do this that anyone could buy. So I quit my job. Moved back to my home country, Sweden, and started a little company called Exotic Matter, and we wrote Nyad along with Robert Bridson, who is a numerical genius, and helped me on well, we collaborated on that, and that basically became, you know, one of the major players really in the fluid simulation industry for a number of years, and then eventually we were kind of acquired into the Autodesk world, and that's why I am now the PM for effects. So what I learned during all those years is, you know, this slide deck needs to be reset, I think. So I will do that right now. Sorry about that. So what I learned during all these years is that doing effects is hard. And basically, let's say you're trying to do a fire effect like Iron Man here. You know, in a lot of shots, you know, you might be faced with, you know, lots of MEL scripts or C++ code or giant graphs to do this kind of thing. And obviously, in some cases, there is a certain amount of complexity that can't be ignored. But in a lot of cases, too, it really should be a point-and-click kind of thing. You should be able to work with these types of effects, in my opinion, in much the same way you might work in animation or in modeling with more kind of direct user interfaces, 3D. User interfaces, and not be forced to always go into these graphs or scripting. And so this is kind of one of the key ideas behind the FX assets, which is driving our vision in effects. So the idea is that on the left you can see a procedural graph, and I'm going to talk a lot more about that in a minute. And on the right you can see these effects. And so let's say that this procedural graph represents a fire simulation, and it's kind of a general you know, graph for that. Then you might use this to, you know, breathe fire or spew fire or burn up a house, that kind of thing. And while building that effect using procedural workflows, you know, may be complex and and sophisticated. The idea being that once it's working, it can be shared and used in many different environments. And the people sharing and using them, or the people using them, wouldn't necessarily have to understand the complexity behind it. So that's kind of the idea, that we're separating authoring from using effects. And for example, one possibility would be that if you're making assets, you could then share them and export them on for example, an asset store on the cloud, or obviously just handing them off to your friends on the local file system, and be able to spread your effects around. So just Einstein, he always said that everything should be made as simple as possible, but not simpler. So the hope is that this procedural graph and the working with that could be made as simple as possible, but of course not simpler, because some graphs are very complex. So another part of the effects assets is the portability that I was kind of talking about, sharing them. So for example, if you did have a fire asset that you had created in Maya procedurally, you might want to use this in 3D Studio Max, and that's maybe you're working on a show, or you're working with another facility that's using Max. So this is the kind of scenario where it's difficult. How do you get these effects across different platforms? Or perhaps you're working with proprietary tools within your own pipeline, or non-Autodesk products. That's another scenario where how do you go from one to the other? Or at render time, your effect really needs to be run as part of a shader or a procedural, or perhaps you'd like to reuse the effect in the game. So these are all scenarios where the portability of effects is a really big problem that I observed over the years. So, if we were to think of an effects asset as a graph that's being kind of wrapped into an asset, if you will, then that asset can take many different forms. So inside of Maya, it could be a DG node that you can play with attributes on, and that's that. And it's hiding a graph inside, but you don't have to worry about that. Whereas in 3D Studio Max, that same graph could be represented by Max node with a similar native interface. And in other tools, whatever type of native interface are in those tools, could be used, even though it's wrapping or referring to an underlying procedural graph or an asset. If at render time, or in code, or in games, that kind of thing, you could imagine that we would have a public API that you could call to say, through C or C++, load this asset and execute it. And that's kind of how we can see all these worlds kind of combining. And the thinking too is Maya would be the primary place where you might author these graphs, but there's no reason why you can't compute them or run them in other places. And not only locally, the other idea too is that we could actually compute on the cloud. Some of these effects could be uploaded and compute on the cloud, and you could also render the data you generated on the cloud. And so the only thing you would be uploading in that scenario would be your assets, and then you would be downloading your final rendered images, which kind of paves the way for sort of a procedural pipeline or an effects-based pipeline on the cloud. The other thing I learned also is that scaling up can be hard. I mean, if you get a nice looking effect, for one house on fire, but taking it to a whole village, it really blows up or puts your hard drive on fire, or your computer. So, essentially, what we really need is scalability and I think smart caching. Scalability is not just being able to compute a really large problem. It's also, once you've computed 38 terabytes of fire, how are you going to push that through the rest of your pipeline? That's a big problem. So the idea of being smart about how much you cache, and cache what you need, and compute what you need, is one big key part of what I think the scalability problem is. And I will talk a bit about how we are thinking about that. So finally, just kind of, what do I expect people to use these assets for? Obviously, simulation is a big part of it, fluid simulation in particular, but also things like destruction and debris and smoke and pulverization, fire simulations, and common things like maybe water effects like raindrops, and interacting with environment, and weather phenomena, tornadoes, storms, and also a situation in which you want to couple all this. So you have water, like a beach, and you have mist from volcano, and you have fluids and viscous fluids, and it's all working together. But also geometric effects. If you want to make a bunch of clouds, one good way to do it is to simulate, using real aerodynamics, the composition and the development of a cloud. But fundamentally, it's the geometric. It's kind of a modeling problem, right? Like you need to make some clouds. It's really modeling, but you could do it through sim or through effects. So that's kind of what I call geometric effects. Another example would be that perhaps you need to model mountain, canyon terrain. One way to do that, instead of just sitting there and trying to model it, would be to actually build, sort of a plateau mesh, and then actually run, basically simulate millions of years of erosion via fluid simulation that speed up time a bit. And you might get a very interesting kind of natural eroded mesh. Again, that's really modeling, but you're kind of doing it through effects. So these are the types of things that I think FX assets can be used for, and many other things. Finally, future workflows. Once we have all these assets and all these components, and they all work together, then the next layer on top of that that would be interesting to explore would be what I call directorial effects, which is similar to, I think, what Warren was talking about when he was talking about directorial animation. The idea that you might be able to click on a monster and click on a bridge and then issue a command, destroy bridge. Obviously, the monster using some kind of pre-canned animation to walk up to the bridge and start banging on it is kind of the directorial animation component. But the fact that the bridge gets auto-rigged and turned into an FX asset so that it can then be destroyed for you based on the animation colliding with the bridge, would be cool. So that's kind of taken it to the next level, but I think, that is the kind of territory we might end up with. And even if you don't like the canned performance or the canned rig setup or whatever, it could also serve as a good starting point for getting, going in and customizing it and making it more how the director wants, for example. So that's kind of the ultimate vision there. So procedural effects in Maya. So the first steps towards this vision that I'm kind of talking about, the FX assets and these workflows, is really actually going to be showing up at some point in Maya, hopefully soon. And the first part of it is really being able to create procedural fluids and particle effects in Maya. So the first thing I'll talk a little bit about here is the scalability through adaptivity. I'll just play this movie. So this is where we're at right now in our labs for Maya. You can see here a foam generation system running on top of a Bifrost fluid sim. So we have an underlying fluid simulation and this particle-based foam that's running. And here's some other settings for the same foam. You can see much thicker, frothier kind of foam going on for those scenarios. Yet again, trying it on waterfalls. And the underlying simulation is not that high resolution here. So you can really see how the foam system really adds a lot of detail to your sim. And the whole thing is running off a single concept, bubbles, really. So whether the bubbles are on surface as foam or underneath, you can see the bubbles coming down under the water there. It really doesn't matter. It's just one system, so it's pretty cool. We're also adding surface tension to Maya now. So you'll see here we get the classic milk crown. So if you need to drop strawberries or anything for commercials, that should work. Kind of the thin sheeting effects there, nice. And we're also upgrading Bifrost with a viscosity model. And we have another more advanced one coming as well, but this is pretty good. We're applying kind of cold air at the surface so it gets dark, the thin parts of the fluid. Adaptivity is one of the ways we want to address scalability. So you can see here on the top, the animation camera flying towards the foam. And then at the bottom, you can see the witness camera. You can see the camera is tracking. As it turns, it's generating foam only within the view frustum. And this is running right now in Maya in our tests. So this is not science fiction, and it's kind of camera-based adaptivity for foam. And you really could extend this to other particle systems too. We're also looking at doing the same thing for the general fluid sim. So you're really high resolution in your fluid sim where the camera is looking. Or in this case, based on distance to surface. So here we can see the voxel grid showing up. Red is really coarse, big voxels, and green are small, high resolution voxels. And we can see that along the surface where you would actually see the water, you're high res, but then in the interior, you're low res, except for around the boundary of the ship. So these are the types of things we're trying to do to address some of the scalability problems. And I think that one of the nice things about adaptivity is not just the ability to reduce your computational problem, but it will also reduce your output that I was talking about before with the file sizes. If you're able to basically do something that would have taken 100 million particles with 1 million particles or voxels, then you only need to write 1 million to disk. That speeds up your file I/O, speeding up your compute, and it also obviously makes management of data much easier, and the meshing problem becomes easier. Everything becomes easier. So So yes, distributed computes, that kind of thing is really powerful and is a great way to address scalability, but we also believe that kind of smart fluid simulation and adaptivity in particular is actually really crucial to control data size. So I mentioned proceduralism. So for the first time ever in Autodesk history, I think I can say, I will now show something that is fully operational, like the Death Star ones, in Maya, which is proceduralism. And so here it has a really low resolution particle sim of a wave. It looks kind of bad, I apologize, but it's very low res. And then we add foam to it, and you've seen the foam before, and here it is, again, low res, so we get some artifacts, foam on the sides there, but you can see the white foam. Now, we're going to open up the node editor and double-click on the container for that foam, and you now see for the first time a real procedural graph right there in the node editor that we opened up. And what we're going to do is we're adding some nodes to multiply by 10 twice, which means multiply by 100. And we're going to multiply the buoyancy by 100 to make the foam particles kind of pop up more, as an example of modifying the graph on the fly. And then we have that if statement there. That's just checking if you've checked a certain attribute. And if you have, then it'll do it. Otherwise, it just passes through the existing buoyancy. So we just wired that up and return to Maya, and voila, you can see the foam kind of spray up, much more buoyant. So we just multiply the buoyancy by 100, all procedurally. And then we'll go back and click on that container and uncheck or check the box to take the other path through that branch in the procedural graph. And so you can see how that's working, and now the foam is going to not pop up as much. And there it goes, more flat to the surface. So well, not live, but a recorded live demonstration of actual proceduralism in Maya for the first time, particle simulation graph. And we just got this going, so we have a long way to go, but it's really exciting because I think this is really going to change the possibilities of working with particles and voxels and meshes and many other things coming up in Maya. And I'd love to get your feedback as we go into this in the fall and the next year. The areas you'd like to see and the kinds of things you might do. So basically just kind of bring it in the context of this talk. So the idea is that this DG node that I double clicked on is the asset really. So basically assets would show up as DG nodes that you can dive into by double clicking and then begin to rewire the graph and make new assets and that kind of thing. So you could share them with other Maya users, you could copy and paste them, or potentially also use them at render time using an API for this kind of thing. That's really the first steps, for getting this story into Maya. The final thing I wanted to talk about before we take some questions is Bifrost versus Nyad. So as you've seen, we now have a procedural graph that's being built, and Nyad was acquired about 2 years ago, and wanted to kind of see what's happened since then. So one of the things that we feel strongly is that Bifrost, with this release that's coming out, is going to be more scalable, not just because it actually runs faster and threads more than Nyad did, but because it is adaptive, which Nyad was not. So I think you're going to see a big difference in scalability there. So that's really exciting. The other one is higher quality. The foam system I just demonstrated is better looking than the Nyad one. Nyad one tended to be a little bit flat and a little bit clumping. So you get some of that thick frothy foam was not really possible or hard to do. And also some of the artifacts and numerical methods that have been updated since Nyad, so they're better looking. It's arguably much easier to use because for one thing it's right there in Maya, so the integration makes it easy. You don't have to export import anymore. But also the point and click interface is great alongside the graph. We also have a more open graph. So the Nyad graph was great, but it did not allow you to open up compounds like I was doing there. So you couldn't go in and rewire the internal workings of a certain node in Nyad, but you can do that here. So at the highest level, the Bifrost graph really is a lot like the Nyad graph with big nodes that do stuff. But when you dive into them, you can see the underlying visual programming language that's really making up all of that. And we really are taking that seriously to the point where we're looking at doing things where if you want to type an expression, that's usually really a pain in the ass to do with visual programming. You got to copy and paste together a bunch of and if and conditionals and stuff. It's much easier just to write an expression as in a script form. So what if you could just do that and then hit enter, and it would just insert a little subgraph of visual programming nodes that represented that expression. So things like that. So we're really working on that, and that's really going way beyond what Nyad did. Nyad also really didn't help at all with rendering. So with Bifrost and Maya, we have a lot of materials and the whole Maya rendering world at your disposal and deeply integrated. So going from sim to final picture is going to be far easier. It's more accessible. We didn't have FX assets, something like that in Nyad. We do here, so that will help. Autodesk is much better than my little company was. We only had 3 guys, so better support and is cheaper. So just kind of putting to rest the whole Nyad journey for those of you that care. This is how I feel about it, and I'm very excited about Bifrost. And that's really the sort of the course of my vision here. We're happy to take some questions if any of you have any. If you do, please line up with the mic so that the guys filming the video can get you get your voice on record there.
Of Bifrost and moving into things like rigid body dynamics, things of that nature, time frames, if you can talk about that.
Sure, absolutely. Great question. The question is, what else, rigid body and other things are we looking at? So we are looking at a whole section of dynamics. Right now, what we've been doing is focusing on fluids. Next up, really, on our roadmap is destruction. So destruction would obviously encompass things like rigid bodies, but perhaps also things like fracturing and pulverization and particle systems for dust, that kind of thing. And that's really going to be the focus after the fluids. As far as the sort of the near future, kind of the same term of release as I'm referring to with the fluids here, you may see some bullet based nodes in the Bifrost graph. It might happen. We're looking. It depends on the priorities and the scheduling, but that would probably be the first thing you would see, and they would interop with the fluids, and also pretty much anything we bring into this world is going to be interoped. And one thing I can talk about is this kind of idea. People talk about unified solvers, where you have rigid bodies, cloth, and fluids, and everything interacting together. And some people take the view that that should be one node that you just like a universal solver node that you plug everything into. And the view we're exploring right now is not that actually. It's more having various solvers that can be wired together to form basically kind of a universal solver. And then that way you can experiment with your own solvers if you're a developer and put that in and have that be part of the whole thing. So that's kind of the long-term vision on that. But as far as sequence, it's really fluids and destruction followed shortly, and then looking at things like cloth and other things. And some of those things like cloth and particle systems are similar to fluids in the sense that they're both based on particle systems, and you're kind of exchanging elastic equations between particles from incompressible equations for fluids. But there's definitely kind of a framework there. So some of these things may show up earlier. And to be frank, a lot of the sequencing we're going to do, like what should we do when and that kind of thing, will really be based on the feedback we get. As we continue to roll the betas of these out to beta customers and special customers, we get the feedback and we find out what people are trying to do, and that may also change things like rigid bodies or not, and when, that kind of thing. But it is definitely in the plan for sure. Yeah.
Hi, Marcus.
Hey.
Can you talk a little bit about the adaptivity of the fluid solver itself? We talked a little bit about the foam and how that's adaptive. Can you talk about the fluid side of it as well?
Sure, to some extent. I don't want to get too technical here, but yeah. So the question is, can I talk a little bit more about how the adaptivity works with the fluid solver? So we are currently, we're very close to finishing that. This is still, I would say, technically in the R&D phase. That's why I didn't show it here. But basically what we're doing is, you saw the different voxel sizes when we did the voxel adaptivity at the end with the spaceship flying into the water. So basically the data structure for the fluid that we're using right now is an adaptive voxel grid, basically, where you can have really small voxels and really big voxels. And we have very simple controls for you to be able to determine what part of the fluid should have the small high-res voxels and what part should have the big coarse voxels. And And so that can actually be programmed through a channel, and you could use the power of the whole graph to actually customize the crap out of that. So you could be tracking things like vorticity or speed of the fluid or other variables, not just camera or whatever, to have a very, very interesting and detailed spread or distribution of adaptivity throughout your fluid. And so yeah, I mean, it's in the pressure solve, the part that Robert Bridson really is working on right now is not having to go dense. Like basically, if the fluid is encoded on that adaptive grid, solving the Navier-Stokes equations on that adaptive grid and not going into any kind of other form. And that really will, I think, lead into many other interesting related, like solids and other things that could be described on a grid. All I'll say about how he's doing that is, it's difficult and probably higher order than linear, but it's definitely perhaps he'll be able to publish it one day. We'll see.
Is there anything that was developed in ice, soft-image ice, being reused or serve as an inspiration for Bifrost? Great question. So, question is, is there how much of ice is in Bifrost really? There's quite a bit. I would say the inspiration for Bifrost really came from Nyad, obviously, due to the acquisition, but also very much from ice, and it's kind of looking at the strengths and weaknesses of both systems. So from where we stand, I guess when we looked at ice, we saw that ice often kind of forced you into the visual programming world too quickly. And some people were complaining that we love ice, but it's kind of hard to use. And I think that might have been part of the reason. The other part of the reason perhaps was that ice was a control flow graph versus a pure data flow graph. So Bifrost is a pure data flow graph, meaning that nodes create data and then nodes operate on it, and like there's actually data traveling through the connections. So if I look at data before a node versus after a node, I can see that the data changed because the node did something. Whereas in ice, it was control flow, so you didn't really have, the connections were connotating more like grammatical structure basically, but the data was actually in soft-image the whole time and didn't really travel through. It was more like I'm wiring up a program and then I'm going to take the whole graph as a program and operate on one object in soft-image. So that, I think, can be harder to understand, and we believe that was one of the reasons why perhaps some people thought soft was hard. So Nyad was pure data flow, and so is Bifrost. So basically, we've taken some of those ideas and changed, but the graph layout, many of the nodes, and very much of the philosophy of how the graph works, other than the pure data flow part, I think ice people will find themselves very familiar with. I know one thing that people talk about is the fact that ice wasn't really effects. It was rigging and animation and modeling and everything. And we're very aware of that. And what we're trying to do is not, I mean, if you go back and look at the history of ice, you see that the first thing they did was particles. They didn't actually do everything else in the beginning. And then they kind of added and expanded. And I think it took them 3 years to get it to the point where it's doing all this stuff it's doing. So given that we just started, we felt, why not do the same thing? So we also are starting with particles and fluids as well to kind of capture the Nyad technology and kind of get a good simulation backbone going. But we definitely are intending to go into many other territories, but very much based on your feedback. So even though this is all happening under the guise of effects, there's definitely a lot of potential to grow outside of what you might call effects. Oh, one thing too, I'll just say, big difference actually between ice and Bifrost. Ice traverses a graph when it evaluates, like a lot of the other nodal systems do. So basically when ice computes, it actually has to traverse through the graph and figure it all out. Whereas Bifrost actually uses a JIT compiler. So essentially the way it works is when I made those changes and I added those nodes to multiply buoyancy by 100, the minute I switched back to try to simulate, the Bifrost system actually looked at that graph, saw that it had changed, and then actually generated, transformed, if you will, the graph into a kind of a code representation, like a program that got compiled on the fly. So when the graph is running and computing, it's not following a graph at all. It's simply just running code that is being compiled as though I had typed it up by hand. So there's absolutely no traversal going on at runtime in Bifrost, and that makes it very different from ice, and is one of the key reasons to why we can get a lot of speed out of it too, because that traversal can actually be expensive.
On the same, I guess, front with the whole idea of working with compounds in ice, I noticed you have the same double click to access the container, access the asset, and then upload it to a store. Is that store online yet? And is it the same idea as the original ice community? Because I think that's where a lot of the original ideas branched out of particle effects. You started getting them into the hands of the community, and then it just exploded from there. Is that sort of the same way the asset store is meant to work, or is it a paper model? Or
oh, absolutely, yes, yeah. Yes. So so it would be free for sure. I mean, I don't want to promise. I mean, this is, you know, some of this is business decisions, but the general idea is exactly that. We want to recapture that community, create an open world where people are sharing assets left and right and doing all that stuff. Absolutely. I'm sure we will also, I think that it should be possible for someone to make an asset and kind of, you know, compile it out and make it binary or something like that, and then be able to make money on it, monetize it. If, as an author of an asset, you know, one should be free to do that kind of thing. And I don't know that, you know, so I think that there might be components like that. And there could also be, you know, components, very sophisticated systems that we might build that we feel, you know, you don't need this, but if you need it, it's a specialized thing, and perhaps we need to charge a little bit if you're going to use it. But in general, I think, you know, the idea is that if you are just making assets and sharing them, that should be a free thing, and, you know, I think we would encourage that. So yeah, I do not see this being any different from the ICE community in that sense. I think I am out of time, but I'll take one more, if anyone has any questions. Nope. Thank you very much. Thanks for coming.